for the delay. But now we can start class. Okay, good news is that did not throw us behind, so. Let's start on, we're gonna finish up 10.5 today, and then we're gonna start on 12.1. And just kind of keep going through. Okay, so today, hypothesis testing for population variances. I'm gonna show you one example to show you what it means, show you an example, show you where you can use it on your calculator. And then I'll leave one of the answers you can look up in your notes, and I'll download those today, okay? That'll get us kind of caught. So population variances. Literally, once again, you're gonna check the conditions apply. Okay, then you're gonna state the null alternative hypothesis, pick your level, same thing as before, okay? Kind of a rehashing. Now, here we go to here. Okay, notice I put a big red caution there and it says, hey, read each example and exercise carefully, okay? Some describe hypothesis tests for variance, while others involve standard deviation. I'm going to give you a formula, okay? And that formula is explicitly just stating variance, okay? But the problem is sometimes the whole question is dealing with standard deviation the whole way through, okay? And so you got to remember, when you have standard deviation to get the variance, you square it, okay? So if you're getting like really odd red bars all of a sudden, that's what's happening is the question is stating standard deviation, but the formula is variance, okay? So having said that, let's jump right back into here. Okay, almost the same thing. Remember, just like we learned in 8.5, we're going to be using the chi-square, okay? Good news is, with this chi-square, you don't have to go look it up in a table. You actually have a button on your calculator that you can use with this one. But there is kind of a little bit of a quirk, okay? See here that still your left tail test, right tail test, and two tail test, they still work exactly the same. Second. Okay, notice you have something a little different though, because if you're not careful, you're going to think of this chi-square as the same thing as your normal distribution, but it's not. Remember, chi-square starts at 0 and looks like that, okay? I say that because whenever you start to deal with this here in just a little bit, what you're going to have to do is realize your lower bounds and upper bounds your calculator is going to give you has changed, okay? So be real careful with that. So look here, for left tail test, we can tell it's going to look like this. But the problem is, when you put this in your calculator, your lower bound is going to be 0 because the chi-square starts at 0, okay? And then this right here is just going to be your test statistic. Same thing whenever you have a right tail test, okay? So once again, you're still going to have a distribution that looks like this. But now, that's just going to be your test statistic. I'm just going to put test. But now your upper here, okay, is going to be that 1e to the 99, because remember, shooting off to infinity there. Okay? And then here, once again, starting at 0 for a two-tail test. Now you just got to be careful on which one you use, kind of a combination of them both. Okay? This is more than just for drawing. You're going to need to know which tail test you're going to use, because when you start putting in your lower bound and upper bound, you're going to need to know, am I starting at 0 and going up to the test statistic, or am I starting at the test statistic and going off to infinity, or so on and so forth, okay? Doing p-values, which is what we'll do today. Okay, when you're seeing the p-value, once again, same song, second verse. P-value of less than or equal to the alpha, that's that area you reject. P-value greater than alpha, then fail to reject. Same thing. Same thing you've done in A2, A3, A4, and A5. Okay, so that does not change. So here we go. Like I said, super simple. You're going to see how easy this is. It's going to be nice because good news is you have a button on your calculator And neither one of your projects require you to draw anything that looks like this. Okay, in your notes, I show you how to draw it, but we won't kind of hang out in that today because we're going to play a little bit of catch up. So I'm going to do this example and then you're going to know how they work, being very careful. Actually, you know what? I'm going to skip this one. Let's get to the one that can kind of fool you. Let's do that one. At a shooting range, instructors can determine if a shooter is consistently missing the target because of the gun sight or because of the shooter's ability. If a gun sight is off, the variance of the distances between the shots and the center of the shot pattern will be small, even if the shots are not the center of the target. A student claims that the sight that it is the sight that is off, not his aim, and wants the instructor to confirm his claim. If a skilled shooter fires a gun at a target multiple times, the distances between the shots and the center of the shot pattern, measured in centimeters, will have a variance of less than 0.33. After the student shoots 28 shots at the target, the instructor calculates the distances between the shots and the center of the shot pattern, measured in centimeters, have a variance of 0.19. Does this evidence support the student's claim that the gun sight is off? Use a 0.05 level of significance. That's your alpha. Assume that the distances between shots and the center of the shot pattern are normally distributed. So first off, we have to realize, how would you know you're going to be dealing with this type of question on your final? I don't know, probably look on here where it says sigma squared. Okay, that's kind of a telltale sign of where you're going to be, what kind of hypothesis test you're going to be giving. That's the good news. You're not having to do this from scratch. Okay, but we need to decide, is this going to be a less than, greater than, or not equal to? Is it less than? What makes you say that?
Because we'll have a variance of less than 0.33.
Very good, right here. That less than, right there. So we know what type of test this is going to be. Yes. This is going to be a left tail test. Now I'm going to give you a formula. You are going to have to use this formula to find your test statistic. You cannot find it by your calculator, okay? So you need this formula. And it is going to be chi squared is equal to n minus 1 s squared divided by sigma squared, or sample variance divided by population variance. So now we got to go to step 2. Step 2, I'll rewrite it down for you. Chi squared n minus 1. What is n? What's the definition of n minus 1? Freedom, exactly. It's your degrees of freedom, which is always your what? Your sample minus 1. Okay, so we need to start figuring out some information here. So, 1. What is my degree of freedom for this one?
27.
27. Okay, now what would I put in next? Looking for sample variance.
Point would be 0.19 squared.
So you're gonna put in 0.19 and then do what?
Then you square it.
Now, why would I square it? What is the definition, the symbol definition for sample variance? That's what? Squared. So why would you square that? It's already a variance. So the symbol for variance is that squared. You don't have to square this one. If had that been standard deviation, square it. Okay, does that kind of, so no, that's why I had that. Read carefully. If it's dealing with variance, you don't got to square it. If it's dealing with standard deviation, that's when you got to square them. Okay, so he is right. It is the 0.19, but we don't square them. Okay, and then what's our population variance? Huh? Variance, population variance.
33.
Exactly, 0.33. Work that out in your calculator. Rounding to 3 decimal places. And yes, this, you're gonna have to do this step on your calculator just exactly like this. Then I will give you the calculator method after this. Now for this number, to figure out your p-value. Okay? You should have gotten 15.4, oops, sorry, 5. Five, 4. Better get that? Okay. That is your test statistic. If we were drawing this, this is where our guy would fall, and we would start looking, does it fall into the rejection region? Does it fall into the fail to reject? Okay. For us to make it easier, I'm just going to just show you today. I'm going to show you how to do the p-value. This is where you're going to need your calculator. So you will hit your get your calculator out. And then you will hit, it is not in the area that you would think it would be in, okay? So be ready. It's not a test zone that you did for everything else, okay? It's your second key. Distribution key. And then you're going to scroll down, okay? And look for the little section that says chi-squared CDF, not PDF. Go one more and go to CDF, cumulative distribution function, because we're adding up all the infinite amounts of probabilities that are in that area. And this is where you need to understand what I was talking to you about. You need to know which type of test you're dealing with, okay? Notice we were dealing with a left-tailed or right-tailed test.
Left-tailed.
Exactly, left-tailed test. Okay, so left-tailed test, look, I got a little chi-square here. My left-tailed test is gonna tell me this is what it looks like. Now, I show you in your notes how you can find out that little chi-square or whatever, but realize chi-square actually does not have an asymptote on its left-hand side. It starts exactly at 0. Okay, so that starts at 0. Then your upper bound is going to be that guy. So notice on your calculator, you're giving some information. It says, hey, give me a lower bound and give me an upper bound and then give me a degrees of freedom. So put in your lower, put in your upper, and then your degrees of freedom. Your lower is going to be the 0. Your upper is going to be that 15.545, and your degrees of freedom is 27. Sacred. With y'all. That number it just gave you, that is your p-value. Okay? And you'll always go and round that to 3 decimal places. So notice my p is equal to 0.39. 0.039, I apologize. But my alpha they give me is right here. Remember, that's your level of significance. So I'm going to put that right there, 0.05. And which number is larger? Yeah, the alpha. So this is larger. And what does that tell us? When the alpha is larger than your p-value, what does that say?
Reject.
Yeah, you reject. Okay, so here I am rejecting that right there. If you actually did this one, okay, the p-value would have fell, or that little test statistic would have fell right in there. Okay, it would have fallen into the rejection zone. So now we know that we're rejecting, we can come over here and realize if we know that we're rejecting, we're confident about that. We can say that that one doesn't mean anything to us and that one doesn't mean anything to us. And so therefore now we at least have turned our answer into a coin flip. So what are we doing? We reject the null hypothesis and conclude that there is insufficient evidence. Okay, or do we reject the null hypothesis and conclude that there is sufficient evidence?
Sufficient.
Sufficient. Always sufficient when you're rejecting the null. Okay, so just be real careful. And there you go. And that's how you're going to do that every single time. Okay, just use that button on your calculator. First off, read it carefully. I can show you very quickly. Look with this one, this right here, notice. I'm just gonna show you the formula again. Notice we're dealing with chi squared, n minus one, s squared, population squared, but look at what everything's dealing with up here. Standard deviations. So when I start putting those numbers into that formula, I need to make sure they're squared, okay? So just be real careful about that. And if you're using variance, you don't square them. That's gonna be the hard part, is remembering, okay, when do I square, when do I not? Remember, very beginning of class, I started saying, hey, be careful of these symbols. That's population standard deviation. That's variance. Sample standard deviation. Sample variance. Okay, so just kind of, when you see that symbol, S squared, that's sample variance, and if they're giving you the sample variance, run with it. You don't have to do anything extra. Good? Feeling okay about that one? Okay. Remember, there is not a chapter 10 test. Okay, so you're good. There is no more chapter test for you. Okay. As I skip over, just remember, I'll have one student reach out, so only one student is taking the test on Friday, which is A-okay. Remember that your final is next week. It will be on, what day is it on again? Tuesday? Monday? Take this class. I think in the morning, sometime after. There's so many. Okay. I think y'all scheduled that. I gotta think about all of them and try to show up. Also, watch out for your project. Okay, remember, I'm changing the due date on that. Not due date, due time. Same day, okay, but I'm moving it back to 5 o'clock. Remember, I've been kind of warning you about that. I'm moving it back to 5 o'clock on Sunday. That gives me a chance to get in there and make sure everybody, if anybody has any problem downloading anything, I'm gonna give you a little bit of grace, but if you email me at 7 o'clock and go, man, my internet wasn't working. That's the first time I've heard from you. And nobody's internet's out that long in town. We're in Hobbs, okay? So try to get, if you can, try to get in early. That always helps. And then I'll send you, your grades will be loaded. Last day to do anything in Hawks is on Sunday night. 11:59, Hawks will shut down completely. Okay? All lectures, I'm gonna download lectures as fast as I can get them out this week so that we have a chance. Okay? So, all right, let's do this one. Scatter plots and correlations.
Oh, this is 12.1, right?
Yeah. 12.1, we skip 11. We don't do 11. 2, 3 questions on your final will come from 12.1. And they're actually super easy. They really are. 12.1 is actually really, it's more concept, but it's a lot of calculator. It's more calculator. As long as you can graph, every single one you should know how to graph by now. Okay, so I mean, got to this class. Okay, scatter plots. You've seen them before, they look like that. Okay? All a scatter plot does is take individual points of data and just start plopping them down. Okay, an X, Y kind of thing. But then we have some definitions we start talking about. An explanatory variable and a response variable. Okay? When I start reading these, kind of go back in your head to college algebra, because something should stick out. Okay, especially when you start thinking about functions. An explanatory variable, also known as the predictor variable or independent variable, is the variable whose fluctuation in value influences a change in the value of another variable. Okay? Remember whenever you had something called f of x? Everybody had that. That x value denoted whatever the x was, what did that affect? The y. You give me an x, I'll give you a y. So therefore, the x value was your independent because you can make it whatever you want. And then whatever you made x, y was dependent on whatever x was. This is exactly the same concept, okay? Because notice a response variable or the dependent variable is the variable that has a value change as a result of a change in the value of the explanatory variable. So easy way to remember this is this. This right here is your x-axis. This right here is your Y axis. Good news is most of the time in your Hawks, it's already going to ascribe an X and Y, even on your final, it will ascribe already an X and Y for you. But what you do need to kind of be concerned about is like if you had to do this for a boss, an employer, or some other time, how do you decide which is which? So how we do it is like which variable affects another one. So let's look at this example graph I got here and notice hours of study. Okay, that's going to be our explanatory. Test scores. Response. Well, why did they choose the X for one and the Y for the other? Well, let's look at it. Does your test score affect your hours of study? Does it? No, listen to that. Does your test score affect your hours of study? No. Your hours of study affects your test score. Notice those are not backwards and forwards. So yes, the longer I study, as we can see from the graph, the longer this student studied, the better their test scores was. Even their lowest test score for 0 hours must be an easy test because they only made a 60. So there you go. That's how that works. Now I say that because eventually on your test and on your homework, it's going to say some things like, this affects this. What do you think? You know, and it's going to ask, what do you think the graph is doing? Sometimes it's not going to give you a graph. Okay, I'll give you an example here shortly. But it's basically saying, when you read that type of question, it's saying, how does this X value affect this Y value? And then you have to decide how it does it. And sometimes there's nothing, it doesn't happen. Like, does me driving fast affect his grade? No, because even if I die, you all get A's. See, there you go. That's kind of how it works. Actually, had a professor die one time. Like literally, Friday we had a lecture, and he's like, "I see you guys on Monday." And then Monday came along, and it was the dean. He said, "Yeah, he died of pneumonia over the weekend, bro." It was very weird. We didn't get A's. They pulled in another professor, so I don't think that happens. Some dude didn't even know how to teach a class. It was sad. So, having said that, look at this. I'm going to give you a bunch of data. Now, good news. On your exam, I don't give you a ton of data, but right now I'm about to. But also good news, you got a calculator. And you have list functions. Okay? So you need to be ready to put things into your list 1 and list 2. But this one, let's take a look at it. Notice we have age and years and height. Which one do you think affects which? Does height affect age? No. What's going to affect height?
Age.
Age. So I would have made age my X value, my height, my Y. At this age, my kid was this height. This age, this height. And then just so on and so forth. Okay. So when you see this as a graph, there it is. And you can even see it with the data next to it. Okay. So notice all we did was just start plotting everything. And that's what you're going to be doing on one question. It's going to say, hey, here's some data. Go in and graph it. And you're just literally going to go, just kind of dot it out. And but that's really not all. Now, one thing that is not beyond the scope of this class is something that got removed about 2 years ago, which I'm thinking about bringing it back. Because you're going to hear the word here in just a little bit. And I go back and forth with how I say it because they've changed wording. But can we all agree that it looks like the older the child gets, what happens to their height? It grows, it gets larger. So if I could draw a line, I'm going to do it as good as I can because I can't draw a straight line on this thing. That's not bad. My iPad does better because if I hold it down, it makes a straight line. That right there is what we would call a regression line or a trend line. Okay? And what it does is it creates a slope. And it says, hey, if I took the mean of this distance here and this distance here, and we averaged it, and we just kind of kept doing that all the way up and all the way up and all the way up, I could create a line. Okay? And this would tell me, hey, what is happening to the data? What am I actually seeing? And this one's pretty straightforward. I'm gonna be honest. That's obviously, if you go back in intermediate algebra, actually not even, let's go back even further. If you were taking elementary algebra at this school or seventh grade math, every single one of you should be able to tell what type of slope is this? Huh? I know it's linear, you're right, but what kind? Positive, negative? Positive, going up, right? So that has a positive slope. Ironically, the formula that you will use eventually would be slope intercept form. Remember that y equals mx plus b? We just change it to ax. Can't use the m on this one. So this right here is called a regression line, a trend line, or whatever. And it's got everything that kind of bases itself off of this right now. So let me show you what it means. Notice, give you two types of positive slopes here. I got a positive slope and then I have got a negative slope. So notice this positive slope here. You can roughly draw a trend line that does that and maybe one that does this. How your homework is going to write this is this has a positive linear relationship. Well, if one is positive, what's the other one? Exactly, a negative. And then we're just going to put linear relationship. Why does it matter? Because your questions are going to ask you something like this. Now, first off, look at it. On the positive, what's happening to the x values? They're increasing, exactly. So what's happening with the y values?
On the positive
On the positive slope. They're also increasing, exactly. So on your positive slope, as x increases, y increases with it. Think about that as a constant of variation whenever you learned that back in like 14.8, okay, in like intermediate. Okay, there is a direct relationship to these things. As one goes up, the other one goes up, okay? So both values increase, both variables increase. What can you tell about the negative slope though? What can be noticed about that? Well, what happens to your x values? Still
increases, but the y value decreases.
Yeah, as x increases, your y value goes down. Okay, so on this one right here, as x increases, y decreases. They have an inverse relationship. Okay, so tell me, without having to think of a graph, what type of relationship would this be? Let's go back to the other one. Time study and GPA. Is that a positive relationship? How?
No, it's a negative.
What would be negative?
Amounts of study compared to GPA.
So the longer I study, what's going to happen to my GPA? It's going to go down. So the x value would be what? The time I study, right? Well, it's going to happen to my GPA. Conceptually, it should go up. So that would be a positive relationship. The x value, time to study, y value, GPA. As one increases, what happens to the other? It increases along with it. And so therefore you have a positive linear regression. There might be some correlation there. Might be. I'll show you about that in a little bit. Here's another question. How about calories eaten and IQ? Positive, negative, nothing? Careful how you answer that one. Somebody's gonna go negative, like you're gonna tell me like obese people are stupid? No, probably no, there's probably none. There is no relation whatsoever. Okay, so notice that one. Okay. Notice. Here's a whole bunch of different types of data. Why would we call the upper left a strong relationship?
Looks like a straight line.
Exactly. It almost looks like a straight line. That's very important to remember here shortly. Okay, and then notice the bottom. It's a weak linear. Reason I say this, we're basing everything off that trend line, right? So if I drew a line here, notice how almost all the data, man, it's like, man, they are almost right on that straight line. There's very little distance in between. But yet, for this one right here, my trend line, when you do the math to it, might be right there. But notice, that one's kind of far. That one's kind of far. That one. Notice the distances that they got to get back to that line. And that's exactly what's happening with that data. That's how they create the trend line. It's creating all these little distances to create this straight line all the way up. Okay? Well, how about here? Why would this be no linear? I want you to think about this. Don't go because it's not a line. Think deeper than that. You're all smart. And I just explained something to you. I kind of gave you a peek behind the curtain. If all these little distances to create that line are distances from that trend line, why would this have no linear? Think about it. And when I tell you, you're going to go, oh yeah, that makes sense. Yeah. If I'm basing everything off distance, couldn't we say all the distances here would be like a positive distance? Right? Because they're up above the line, right? What are all the distances down here?
Negative.
Wouldn't they just cancel each other out? This distance canceled that distance. This distance canceled that distance. And they just eventually canceled out everything. And so you've got zero. Now there's not, you can't even create a line with that one. It would not create a line. You'd be like, nope, there's no trend line. There's nothing for me to calculate. I can't do it because this thing does not create one. And then obviously nonlinear relationship, that's kind of a duh. Okay, just to look at it. That'd be more of a parabolic relationship, which we don't study that in statistics. Okay. Well, you do, but not in this class. Okay. So now, what does that matter? Well, and this is actually kind of a fun part because I always like the mathiness of it. Look here, I'm going to give you a little word. Definition, Pearson correlation coefficient, which you will have to know for your final. The Pearson correlation coefficient P. Now, very quickly, see that little P? Notice it's not the letter P. Okay, that is an italic P. Okay, so I usually write that one like this. Notice how I kind of make it look a little fancy. That is actually the lowercase symbol. It's a Greek symbol and it stands for rho. Okay, not to be confused with what? P, which stands for what? Proportion. Be real careful about that, okay? Italic P, rho, stands for the Pearson correlation coefficient, is the parameter that measures the strength of a linear relationship between two quantitative variables in a population. The correlation coefficient for a sample as denoted by R, okay, that's going to be the mathy, that's going to be your answer, okay, is always a value between -1 and 1 inclusive. Inclusive, remember, means you can include the endpoints. So you can include the -1 and you can include 1 and all the infinite numbers in between there. There's what it means right there. So I give you data. I give you a lot, I give you a little, doesn't matter. I give you a lot, use Excel. If I give you a little, use your calculator. Okay? You start working out all the data, you put it all in your calculator, and it's going to give you an R value. Okay? R value, and we'll give you a little sketch here. R value of -1, of exactly -1. We're going to go exactly -1. will look exactly like this. You notice how all my data points, what they do? They created a negative slope and they are all perfectly in alignment. There's not even a one that's wavering off. It is all just perfectly in a line. Well, if I get a one, same thing as before. Let me go and put a y over here. X, y, x. Here, same thing. Boom, 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 boom. All perfectly in a line. And then just like you saw in the last one, if you got a 0, that's the one that looks like this. Where it really have like no linear relationship. Good so far? Kind of makes sense a little bit. You'll see a lot better once we do an example. So get up your calculators. Go to your list of functions, make sure it's cleared out. And I want you to start typing in that data. And I gave you a lot because I want to see how well you do on it. I will follow along with you. And we're going to start, now notice on this one, they give you an X value, they give you a Y value. But how you're going to do this is going to be your list 1, and this is going to be your list 2. So remember, you just go to your stat, edit, make sure your lists are cleared, and start throwing in that data very carefully. Okay. When you're done, I need you to, I don't know what they've done to your calculators. Okay. Most of y'all got your calculators from the tutoring center, right, or the high school, something like that. Okay. I don't know if they reset those, so you need to do something with your calculator real quick. I'm gonna pull it up here on the screen and I will help you. Better to check it anyways, okay? Before you try to do what I'm about to show you how to calculate all this, you go into your calculator. So what you're gonna do is I need you to hit your second key again, then you're gonna hit 0. Okay, that's gonna take you to the catalog. Okay, those are all the functions that your calculator could ever possibly do. Okay, you need to scroll down and go to where it says diagnostic on. Hit enter. Okay, you're gonna have to hit it twice just like it says. Okay, you have to do that. Now, we could have gone through the whole process of me showing you how to do this button first, but if it didn't show you, why do that? Let's go and make sure everything's on. So did everybody do that? Okay. So now what you're going to do to calculate all this data that you just put into your list functions, you're going to need to hit stat once again. But now we're going to scroll over and hit calc. And then you're going to scroll down and you're going to be looking for the title that says linear regression. Now be real careful because you probably are seeing 2. Look for the one that has AX plus B. Okay? That count. Once you hit that, just hit enter all the way through. There's nothing you need to put in there because you've already put in stuff into your list 1 and your list 2. So it's all the way through. And you should be getting a Y, an A, B, but you should also see an R squared and an R. Is everybody getting that? If you didn't, go back and check and see if your diagnosis is on.
I do that again.
It's down at the bottom. Everybody good on that? Did you get the R squared? Okay, good. Your calculator does not just automatically turn that on, so be real careful about that, okay? If you didn't get it, you might have went and accidentally turned it off, so go back in and do it again and turn it back on, okay? Notice it gives you an R right there at the very bottom. It gives you an R. And you're always going to round to 3 decimal places when going to R. That is the rounding rule for R. So for this one right here, notice you get a positive 0.980. Now tell me, knowing what I just told you about the linear lines of between -1 and 1, would this be a positive slope or a negative slope? How close would all the data fit to that line? Decently close. It's 98%. Look at that. A perfect score where everything lined up perfectly would be a 1. This is 0.98. Okay, is that going to help y'all see how this is working now? So you don't even have to plot all your data and find a regression line. You can go, oh, all my data sits really, really close to this line. So this is going to work out. By the way, if you know anybody that's not here today, please help them out whenever you get with them again on their calculator, so that way you can help them if they're not here today. Did everybody get that? Did you get it? What's it? Did you do this part right here? Can you see what she's doing on Hamilton Fest?
You do what?
I want to make sure everybody gets it because you cannot. I can show you the formula to this. Yeah, it's ugly. It's extremely ugly. It's got like 7 summations in it. Okay, so let's make sure we're getting the calculator down. Okay, because I think your book does say, hey, you want to do this by hand? And I'm like, who would want to do this by hand? Nobody. No statisticians are sitting there going, you know what I'm gonna do today? I'm gonna do some math by hand. Just so I can really start screwing with the American public. No, doesn't happen. Good on this one?
That's it.
You get it? Perfect, good deal. All right, so testing the correlation coefficient. Well, here's what it matters, okay? Testing the correlation coefficient for significance. Look at this little symbol here. It said the sample correlation coefficient R is statistically significant. Okay, if the absolute value of R is greater than or equal to the R of alpha. You're gonna have to know how to use a chart on this one. Okay. Your table will be given to you in Hawks on your final, and I'll also give you papers. For the proctoring socks, I'll be emailing the papers, but they also have them on their Hawks board as well. So look here, let's do an example. First off, do me a favor, put that data into your calculator. You just did it with a whole bunch of data. Now I'm only giving you pop. That's simple. So let's do it again and see if you can calculate me an R value.
It's R.
So the diagnostic, we just have to do it one time, and after that, we're set.
What's that? Yeah, you only gotta do that one time and then your calculator, it's gonna be on forever, okay?
For R to be statistically significant, it has to be greater than or equal to what again?
An alpha. It looked like this. R has to be greater than or equal to R of alpha. And I'll show you what the R of alpha is very, very shortly, okay? It'll make more sense whenever I show you. Right now, I just want you to find R.
(0.95).
Carefully. Negative 0.985. Your negatives are very, very small. Okay, so you gotta watch out. So look at them very carefully, okay? So you're right. We have an R value here of negative 0.985. Now realize what this says. You know nothing yet, okay? Now it literally says this, do not confuse this number with your alpha. It is not your alpha. You're gonna have a table to look this up on. okay? So notice it says the absolute value of negative 0.985. Well, the absolute value of any negative is always a positive. Very good. So that's just going to be 0.985. And I need to find out if that's greater than or equal to something. Well, good news. There's your calculus. There's your chart. Let me erase that little alpha there so we can see better. And notice here, the very top of it, I've got an alpha of 0.05 or an alpha of 0.01. Well, I've also got samples. How many samples do I have? 5, exactly. So I'll come in here and I'll look at the 5. I also notice I'm looking at this 0.01. Where do they match up at? Oh, look right there. 0.959. So is 0.985, and I've got 0.959. Which one is larger?
985.
Yeah. 985 is larger. Remember what this says. If the absolute value of R is greater than or equal to R of alpha, it is statistically significant. So this becomes a yes. So it matters. That's what it's saying. That data matters. There is some significance to this data and it matters. Good so far? Okay. Definition. Testing the correlation coefficient for significance. Still testing it. The coefficient of determination, R squared. First off, don't freak out. You've already been figuring it out. Didn't you? Didn't your R value right above it have an R squared? It gives it to you. Okay? Or you can square your R value. Just remember, if you're going to square your R value, please make sure that you're calculating it at 4 decimal places and then squaring it instead of trying to square it from the 3 because you will get it wrong. Okay, so be very careful about that. Well, here it is right here. It's right above your R. Okay. Well, what is it? Okay, let me show you something. This one's actually kind of nice. Okay. If I'm going to give you just a hypothetical. Okay, let's put it this way. If I have an R, we're not going to use those numbers. If I have an R value equal to 0.8. First off, conceptually, we're doing concept right now. You're still in statistics. I do not want you leaving this class and just going, well, I know how to calculate standard deviation. No, I want you to know what a standard deviation is. Okay, I want you to be able to hear the news at some point in time, and when they say, this is plus or minus 1 standard deviation, you can go, okay, well, that's about 68%. You know, you can kind of walk away, have a little bit of knowledge to walk away with, okay? I get it. You're going to lose all the hypothesis testing. Probably going to lose those eventually. I get it, okay? Even I do. I have to kind of remind myself. But I do remember certain little things. So if I said I just calculated some data, and I'm going to pretend I took all his grades. I found out the time that he studied, and I found out his grades. I plotted them all every day, whole semester. I looked at all his homework, said, hey, man, how long did you study? He was truthful. He turned it in. There you go. At the end of this, I found an R value, 0.8. Okay. What is that telling you about the data right now? Is it a positive or a negative? Go with that.
Positive.
Positive, okay. So there is a positive relationship, isn't there? It's saying, hey, the more time he studies, what? The better his grades were. Well, is it a strong linear relationship or is it a weak one? Look at your number. What is it saying? Is it a 1? No. But it's also not a what?
0.
Not a 0. It's not even 50%. I would say it's moderately strong, right? I mean, okay. Well, then I look at his R squared. Now, this is what I like. R squared is obviously going to be 0.64. This is what it means. Now, read what it says. The coefficient of determination, R squared, is a measure of the proportion of the variation in the response variable Y that can be associated with the variation of the explanatory variable X. Y'all get it? Y'all understand that perfectly, don't you? Sure you do. This is what it's saying. If, okay, 80%, this is my X, of the variation in Y can be explained by X. Now let me put that in English for you. We use his numbers again, right? We know that I studied his amount of time he studied. There's my explanatory variable, right? The response variable was the what? His grade. I matched them all. I found an R value of 80%. Okay? 0.8. This is what it's saying. 80% of his grade. Hear me as I say this, because once I say it, hopefully it makes you go, oh, okay. I can explain away 80% of his grade to him studying. I can go, okay, yeah. Surely, yeah, his grades got good because look, I can look at the amount of time he studied and his grade got better. 80% of that explains that. Well, what about the other 20%? I have no clue. I don't know. There's something else out there that caused him to do that well. I don't know what it is, but it's there. Well, now think about it. What if I gave you a response variable of like 0.2? That's only 20%. But what if it still showed a positive slope? Okay, it'd be slight, wouldn't it? It wouldn't be like a heavy, heavy slope, but it'd be slight. Wouldn't I kind of go, oh, you know what? I can only attribute 20% of your grade to the hours you studied. There's 80% going on that I don't know. And that's either A, innate ability. Maybe he's just really, really good at math. You know people like that. They're just like, yeah, I looked over the test about 10 minutes before I came to class and they make 100. And those people, you just want to throw them in front of a bus. Okay? Or he's cheating. Because I can only explain away 20%. There's an 80% out there I have no idea. There's some sort of other variable that I'm not accounting for. That's what that R squared tells you. It says, hey, that's 64%. This can explain some things. But there's still that other portion there. I just don't know. So that's what R squared says. So whenever you're getting these R squareds, don't just put down the number and walk on. I get it. Realize, go back and look at the question and go, okay, this is saying this. I know this. But this is how much unknown is out there. Now, granted, if there was a 1, had he scored a 1, how much unknown? Dude, none. If I get an R value of 1, how much does that leave? 1 squared is 1. How much unknown is it? His whole scores are based off how much he studies. That's it. So that's what that R squared tells us. So, good so far? All right, let's stop there for the day. We'll come in next class. I'll do some homework examples, and then we're going to finish up with 12-2, and then